You've probably heard the line, "Most of the universe is dark matter." It sounds like a fact. It's actually a confession, because what that sentence really means is, we see gravity doing something, and we don't know what's doing it. And if that doesn't bother you, you've been hypnotized by scientific vocabulary. Here's the setup: clean, simple, and slightly humiliating for our species. In the last century, physics gave us two masterpieces, two instruction manuals for reality. Manual number 1, General Relativity, Einstein's upgrade to Newton. It tells us how gravity behaves on the big stage: planets, stars, galaxies, the whole cosmic architecture. It doesn't say what gravity is, it says what gravity does. Manual number 2, Quantum Theory, the bizarre rulebook for the small stage: atoms, particles, the ghost world beneath matter, where common sense goes to die. Both manuals work insanely well until they meet each other. And when they meet, they don't shake hands. They throw chairs. Relativity breaks down in places we most want answers. The center of black holes, the first instant of the Big Bang. That's where the equations start spitting out infinities, like a slot machine stuck on error. Quantum theory, meanwhile, can describe three forces with clean mathematics. But gravity refuses to join the party. So we're stuck with a reality that behaves like it has two operating systems. One for the big, one for the small. And they don't speak the same language. Now add the weirdest part. Even if you ignore black holes and the Big Bang, the universe still doesn't add up. On galaxy scales, stars orbit as if there's more mass than we can see. Galaxies bend light as if they're wearing invisible armor. The early universe's afterglow carries patterns that imply extra gravitational scaffolding. We gave the invisible culprit a name: dark matter. And we've spent decades hunting it like it's a missing suspect. But what if the suspect is the detective? What if dark matter isn't a new kind of stuff at all? What if it's gravity itself wearing a mask, and the particle that carries gravity, the graviton, has been the real mystery the whole time? Let's talk evidence, because this isn't a bedtime story. It's an audit. The first red flag is galaxy rotation. In a normal, honest universe, the farther you get from the center of a galaxy, the slower stars should orbit, because most mass is in the middle. That's how gravity works. But when astronomers measured it, the outer stars were moving too fast, so fast that the visible mass can't keep the galaxy bound. If the math is right, galaxies should be flying apart. They're not. So either there's extra mass, or gravity behaves differently than we think. Second red flag: gravitational lensing. Mass bends space-time. Space-time bends light. So when a cluster of galaxies sits between us and distant light, it distorts the background like a cosmic magnifying glass. When we map that distortion, we can infer how much gravity is present. And again, the gravity is stronger than the luminous matter can explain. It's like seeing footprints in snow that clearly belong to an elephant, while the zoo swears it only owns cats. Third, the cosmic microwave background, the oldest light we can detect. Its tiny temperature ripples carry information about how matter clumped in the early universe. Those ripples match a universe where invisible mass helped structure form. Without that extra gravitational scaffolding, you don't get galaxies on time. You get a universe that stays too smooth for too long. So we built a profile of the invisible thing. It must be cold enough to clump. It must be mostly collisionless, because if it slammed into itself a lot, our simulations and observations wouldn't match. It can't be charged, can't glow, can't block light, and it barely interacts with ordinary matter. Then comes the awkward fact. We've searched for these particles directly. Underground detectors, space telescopes, particle accelerators, like setting traps in every room of a house. And the intruder never shows up. That's where people either get honest or they get religious. The honest response is, maybe we're hunting the wrong animal, because there's a second way to explain extra gravity, not by adding invisible mass, but by questioning the thing we treat as a finished product, gravity itself. And that's where the graviton enters, quietly, like a suspect who's been sitting in the interview room the whole time. Now, the mainstream approach is to say, fine, dark matter is a new particle. WIMPs, axions, sterile neutrinos, hidden sectors, a whole invisible menagerie. And sure, nature might have extra ingredients. But notice the psychological pattern. Every time we fail to detect the particle, we don't reduce our confidence. We expand the list, we add complexity, we build a bigger zoo. The graviton idea is nastier because it doesn't let us escape that way. It says, stop adding animals. Look at the cage. If gravity is quantum, like the other forces, then a messenger particle isn't optional. The graviton becomes a consequence, not a fantasy. So why hasn't it been detected? Because gravity is absurdly weak on quantum scales. A fridge magnet can defeat the entire planet's gravity in your kitchen. That's not a metaphor. That's you casually humiliating gravity every day. In particle terms, weak interaction means rare events. So rare that even absurdly sensitive instruments might see nothing for decades. That silence would look exactly like the dark matter problem. Something is there gravitationally, but it refuses to shake hands with our detectors. Now, here's the key dark matter in disguise mechanism. Dark matter appears cold and clumpy. Massless particles usually don't clump. They race around at light speed and smooth everything out. So if gravitons were perfectly massless, they'd struggle to behave like cold dark matter. But physics allows a loophole. A tiny graviton mass, still within observational constraints, could make gravitons move slower, lose energy differently, and potentially clump into halos over cosmic time. And if that makes you uncomfortable, good, because it gets worse. Dark matter also appears collisionless. It doesn't ram into itself much. Gravitons would be the ultimate collisionless particles. They'd barely interact with anything, including each other, except through gravity, which is the weakest handshake in the universe. That means, if gravitons were dark matter, detecting them directly might be borderline impossible. Not because we're stupid, because the universe is rude. And then comes the twist that feels like cosmic sarcasm. We have already seen gravity moving through space as waves. Gravitational waves, ripples in space-time from black hole mergers, are real. We've detected them. In a quantum description, those waves would correspond to huge coherent bundles of gravitons. Not a single particle pinging a detector, but a tidal chorus. So imagine the humiliation. We might be swimming in a graviton ocean, hearing its roar in gravitational wave observatories, while still failing to catch even one graviton by itself. It's like proving the existence of rainstorms while insisting raindrops are a myth. So, case closed. Gravity is dark matter. Not so fast. The universe loves to hand us a beautiful idea and then punch it in the mouth. Here are the objections, the ones that actually matter. First, cosmic expansion. As the universe expands, radiation loses energy, light redshifts. If gravitons behave like radiation in many contexts, they'd also lose energy over time. The question becomes, can they remain cold and abundant enough to form halos without fading into irrelevance? Second, the speed of gravity. Observations strongly suggest changes in gravity propagate at or extremely close to the speed of light, but massive particles can't travel at light speed. So, if gravitons have mass, how do you preserve the observed behavior? That's not a nitpick. That's the central plumbing of the theory. Third, is gravity even a force? Relativity treats gravity not as a traditional force, but as geometry. Mass warps space-time, and objects follow curves. If gravity is geometry, what exactly is a graviton carrying? Are we quantizing the fabric itself, or are we forcing a particle picture onto a geometric phenomenon? These are not easy questions. They are exactly why this mystery survives. But here's the value for you, the non-physicist who still has to live in a world full of people confidently bullshitting. A name is not an explanation. Dark matter is a placeholder, not a victory lap. An explanation must do three things: fit existing observations, make new predictions, survive attempts to kill it. That's the difference between science and vibes. So, what would graviton as dark matter predict? It would imply subtle signatures in how structure forms, how gravitational waves propagate through cosmic distances, how halos behave, and how the early universe clumped. It may also constrain the graviton mass so tightly that the idea either becomes elegant or impossible. And here's the brutal honesty. It's possible the universe doesn't owe us an answer we can measure directly. Some particles might be, in practice, undetectable, except through their collective effects. That's not failure. That's reality being bigger than our tools. But we're not done, because there's an even more offensive possibility. What if there is no dark matter at all? What if we're watching gravity misbehave on large scales? Next episode, we step into the rival camp, the people who say the universe isn't hiding invisible mass. We wrote the gravity rules wrong. Modified gravity. Monday, emergent gravity. The theories that claim dark matter is a mirage, and if even one of them is right, it means for a century we've been staring at the universe like a detective with the wrong suspect board. Subscribe, because the next question is not what is dark matter? It's what if gravity has been lying to us the whole time?